All right, this problem is a flux integral. All right, so we want to find f dot ds. The f is the amount of fluid flowing through, and that'll just be the density of the fluid times its velocity. So f will be the density times the velocity right, like the wind. It's got a certain density, certain direction, that'll push a certain way. If you increase the density, say made instead of wind, if it were a water wave with the same velocity, that'll be a lot more particles flowing through the same region in space. All right, the normal for a sphere, unit normal, is just, since it's centered at the origin, x, y, z divided by its radius, so it'll be 2 for this sphere. So if I look at the dot product, f dot n is going to be, put it this way, negative 21y, 21x, 42z dot x, y, z over 2. And we'll get negative 21xy plus 21xy plus 42z squared all over 2. So 21z squared. And our flux integral is going to be, of course, f dot the unit normal ds. So this will just be the integral of 21z squared ds. Now with a sphere, I always simplify it in Cartesian, but now I will go to parametric, and it's the full sphere, so we'll have theta goes 0 to 2 pi, phi goes 0 to pi, z is the radius times cosine phi, that gets squared. ds, we might know that r sub theta cross r sub phi is going to be the radius squared sine phi. So I'm just going to get 2 squared sine phi. And now I'm integrating d phi, d theta. So if I gather my constants, well, I got 4, 16 times 21 times 2 pi. So we'll say 32 times 21 times pi. I have to integrate 0 to pi of cosine squared sine phi d phi. So that'll just be, what 32 times 21 is 640 plus 32. So maybe 672. Cosine cubed over, if u is cosine, it'll be the negative of cosine cubed over 3. 0 to pi. And that'll actually just give me a 2/3 total. Let's see, I had a 3 here. I just could have made this 64 times 7 times pi. So 420 plus 28. So that would be our calculation.